Okay, everyone, let's wait for 2 more minutes. Okay, let's wait for 1 more minute. Okay, in the interest of time, let's start. Okay, good afternoon, everyone. Welcome to the second session of our theory day. So without further delay, let's start with our first speaker today, Arpit from Justin's group. So I think you are the co-host now. So you can share your screen and let us start. Okay, so every one of you will have 15 minutes in total and try to finish by maybe 12, 13 minutes, and we'll have a few minutes for questions. Okay, so yeah, Arpit, you can start.
Okay, hi everyone. I'll be talking about strain-induced large injection currents in twisted bilayer graphene. So here's a brief overview. I'll be talking about the photoresponse to circularly polarized light in magic angle twisted bilayer graphene. And we find that there are large injection currents in the terahertz regime, which are extremely sensitive to strain, degree of alignment between graphene and HBN layers, and chemical potential. We argue that these occur due to large interband Berry curvature dipole density between flat and remote bands. So before we get started, let's motivate ourselves. So an obvious motivation is that photocurrents are always useful to unravel the material properties. And a very recent example is that injection current was used as an experimental probe for Berry curvature. And in context of twisted bilayer graphene, we say that since injection currents are extremely sensitive to strain and the degree of alignment between graphene and HBN layers, they can be used to probe the degree of symmetry breaking in realistic twisted bilayer graphene samples. And why this is important? Because it's been known that different twisted bilayer graphene samples show different phenomena. And a very well-known example is that of superconductivity and an anomalous called plateau, which are not seen in the same samples. So let's begin with injection current. Injection current is a bulk photovoltaic current due to asymmetric transition of velocity during the interband transition. It is a second-order response in applied electric field and therefore present in only inversion asymmetric materials. It requires a finite relaxation time to saturate the injection of electrons and holes. Now, since it requires a finite relaxation time, we will define the rate of current instead of the current itself. And given an electronic system and the incident radiation, we know that light-matter interaction can be described using Fermi's golden rule. And what we find is this injection current rate, which has the following dependencies. Number one is the change in the velocity during the interband transition. Of course, that goes by the definition itself. Number two is the difference of Fermi function of initial and final states. And number three is the interband Berry connection, which is given in terms of the velocity matrix elements. Now, two final comments for the injection current, that it's only non-zero for inversion asymmetric materials, and for time reversal symmetry, it's non-zero only for circularly polarized light. Now with this, let's come to injection current in twisted bilayer graphene. Now since twisted bilayer graphene preserves inversion symmetry. Therefore, our interest is only in injection currents due to circularly polarized light. And what we find is that this rate for injection current is given in terms of a special commutator, which we define in this way. And we'll show that this actually plays a very important role in explaining the injection current physics for multi-band systems, such as twisted bilayer graphene. So before we jump into the calculations, let me give you some intuition by symmetry analysis. So let's begin with pristine twisted bilayer graphene. Now it obviously preserves time reversal symmetry and is also inversion symmetric by the virtue of these 3 point group symmetry, which are C2Y, C2Z, and C3Z. Again, since it is inversion symmetric, we expect that there should not be any injection current. Now, an obvious way to break inversion symmetries to align the graphene layers by boron nitride. And what it does, it breaks inversion symmetry by breaking C2Y and C2Z symmetries. However, we still do not get injection current because C3 symmetry still doesn't allow it. Now to get rid of the C3C symmetry, what we do is we apply strain to the heterostructure of twisted bilayer graphene and HBN. And now we get rid of all the point group symmetries, which allows a finite injection current. So with this, let's describe the system that we are dealing with. So the system is of twisted bilayer graphene, which in the quantum limit can be described using the Dirac Hamiltonian of 2 layers, which is coupled using an interlayer coupling potential. And here we consider the effects of lattice relaxation as well, therefore taking different values for AA and AB sides hopping. Now to include the effect of alignment of graphene layers. The AB sublattice twisted bilayer. We started with pristine twisted bilayer graphene Hamiltonian. We introduced a sublattice direct potential. Now the effect of strain goes into the Hamiltonian in 2 ways. Number one is the geometric deformation part, which is straightforward, that strain deforms the real and reciprocal space lattice vectors. And number 2 is the gauge field that effectively describes the motion of electrons, low energy electrons in strain. So what we have is a new Hamiltonian with strain, with sublattice symmetry breaking, and this is what we use to get the injection current in twisted bilayer graphene. And what we get is the following. Number one, we have these peaks in the injection current, prominent peaks in this injection current in the terahertz regime. Number 2, it's extremely sensitive to the chemical potential. And for example, if we place the chemical potential deep in the remote bands, we see that the injection currents are quite suppressed. Now, if we place the chemical potential between the flat bands, we find that the injection current is still suppressed. However, if we place the chemical potential inside the flat bands or between flat bands or remote bands, we find that there are these high value injection currents found in twisted bilayer graphene. And here's a more detailed analysis of injection current with variation to chemical potential. And we fix the photon energy at 20 MeV for this calculation. And what we find is that indeed, on 2 sides of the charge neutrality, the injection current has an opposite sign, and the maximum values are obtained when the chemical potential is placed within the flat bands. So to explain these complexities related to the twisted bilayer graphene injection currents, we recall the formula for the injection currents in presence of a circularly polarized light. We found this special commutator, which is related to actually the band resolved Berry curvature. And we define the product of band resolved Berry curvature and the difference of the velocity during the interband transition as the interband Berry curvature dipole density. This is actually an interband analog of the Berry curvature dipole density, which is given as a product of velocity and the Berry curvature of a single band, and it's very useful to describe the nonlinear Hall effect. So now here's a brief illustration. What we do here is we take the most dominant transition as a representation, and what we find is that the interband Berry curvature dipole density has very high values for transition between valence remote to valence flat bands and conduction flat to conduction remote bands. Now this actually explains why we get pronounced injection currents in terahertz regime, because since the transition takes place between flat bands and remote bands, it's evident from the energy gap here that the injection currents are pronounced in the terahertz regime. Now it also explains why why injection currents are so sensitive to the chemical potential. Because depending on where we place our chemical potential, accordingly the charge carriers the charge carrier excitation will take place. Now let me illustrate this with an example. So let's say we have the injection current along y direction, and we place the chemical potential deep inside the remote bands. Now, although we allow this green transition to take place, which has a peak in this interband Berry curvature dipole density, however, this peak is confined only around the gamma point, and the iso energy surface for this orange Fermi line is actually confined. Makes the transition confined away from the gamma point, and this can be seen in this injection current figure that correspondingly orange line injection current is extremely suppressed. Now let me give another example that now I allow the transition to take place around the gamma point. So what happens is that between the chemical potential between the flat bands, we find that still the injection current is still suppressed. And why does this happen is because there's kind of a partial compensation going on. And how we can see that, if we consider this purple and yellow transitions here, we can clearly find that as we span the entire Brillouin zone, they almost cancel, they partially compensate each other. And as far as this flat band to flat band transition is concerned, this compensate itself as we span around the entire Brillouin zone. Now, however, these compensation effects are avoided when we move away from the charge neutrality. For example, if we place the chemical potential here between flat band and remote band, we can see that there is this green transition which is peaked here at gamma point and gives rise to a large injection current denoted by this pink line. Now, if we move the chemical potential to the other side of the charge neutrality, what we find is that this black line actually is now opposite. Has the opposite sign to this pink line. And why? Because this blue dominant transition peak here has an opposite sign to this green one, which gave rise to the injection current for this pink line. Now this clearly explain this clearly explain the use of the interband Berry curvature dipole densities to unravel the physics of injection currents in a multi-band system like twisted bialloy graphene. Now let me make some final comments about how large these currents are. Now to compare how large these currents are, I actually calculate the susceptibility, which is independent of the electric field. And what I find is that the susceptibility corresponding to this highest magnitude of injection current is 10 to the power 12, which is actually 2 orders of magnitude larger than those found in ferroelectric GES, which is already an acclaimed material to show large injection currents. So with this, I thank you all and leave you with injection currents in twisted bialloy graphene, which are extremely sensitive to symmetry breaking mechanisms and chemical potential. Thank you.
Okay, thank you, Arpit. Any questions from the audience? Arpit, can you just quickly summarize? So what are some of the special properties of TBGs that makes this large injection current, or this? Why are you choosing TBG for this particular study?
Okay, so why I'm choosing twisted bialloy graphene for this particular study is because of these flat bands. So if you note here that these flat bands actually offers a high density of states for strong optical absorptions to take place. And since injection currents is an optical phenomena, it actually occurs due to the optical absorption. Therefore, we expect that these numbers should be large in twisted bialloy graphene. So what started as a quest to look for these large numbers, we found that these injection currents are extremely sensitive to the chemical potential as well. And therefore, it's not only the flat bands that are important, but it's also important that where we place our chemical potential.
Okay, so if I have a different system with a flat band, do I normally will see the same thing that you're seeing here, or is there something else? You mentioned about the chemical potential. Does it depend on the dipole of the Berry curvature you mentioned just now?
Yes, it would depend on it definitely would depend on the Berry curvature dipole that I defined here. But again, this dipole actually depends on a lot on the system details. While flat bands are expected to have strong optical absorptions, But depending on the symmetry breaking mechanisms, as I said, there are two kinds of symmetry breaking mechanisms here. One is we break the AV sublattice symmetry by aligning the graphene layers with hexagon boron nitride. And there's another symmetry breaking effect we apply as strain as well. So depending on how strong are these symmetry breaking mechanisms in other systems, and so of course the flat bands can give you high optical absorption, but depending on how strong are these symmetry breaking effects in other systems, we can figure out how large can these injection currents be.
Okay. So can I say the three ingredients are the breaking of symmetry, otherwise there's no current. Then
Yes.
You have high density of state with flat bands, and also the band geometry, which is probably the dipole of the Berry curvature. These are the three ingredients that are important.
Yes.
For injection
Yes.
current.
Yes.
Okay. Okay. Good. Any other questions from the yeah, Pinaki, please. You don't have to raise hand. Just unmute yourself. Pinaki, we can't hear you.
Okay. Hi.
Okay.
Thanks.
Yeah.
Hey, Arpit,
Yes.
the effects of symmetry breaking, in particular strain, is it to increase the Berry curvature or is it also for the current?
So let me just go back a couple of slides. So since this commutator that I defined actually is a band resolved Berry curvature, and we know that the more gap we can create by closely aligning the graphene and boron nitride layers, the larger Berry curvature we are bound to get, and this will eventually result in a larger injection current induced by graphene.
Okay, thanks.
Great. Any other questions from the students?
Hi, Arpit. I have a question about the Hamiltonian. Means what kind of process are you using this light absorption? Means is it what kind of process? Can you show the Hamiltonian? Means the coupling between light and
okay, the coupling between light and so here is the coupling between light and yeah. So simply what I do is that I'm using Fermi's golden rule. So the light matter interaction goes in this form. We have some velocity coupled to the electric field. So it's kind of P dot A term that goes in here into the light matter interaction.
I see. So is it a classical wave, right? Classical wave coupling to the electrons. Means is it? It's like the normal. I see. Okay, it's fine. Okay, yeah.
Not sure it's classical because Fermi's golden rule is quantum mechanical itself.
It's semi-classical actually. The system you're doing is quantum, but the wave you're
yes, correct.
So okay, thanks. I understood.
Okay, great. In the interest of time, let's move on to the next speaker. Our next speaker is, I think, from Tsinghua group. Shen Ruizhe. Okay, can you share your screen, please?
Yeah, sure.
Mm-hmm.
Okay, shall I start?
Yes, please.
Thanks. Good afternoon, everyone. It's my pleasure to give this presentation here. I'm Ruizhe from Professor Tsinhua's group. Today, I will talk about our recent research on the non-Hermitian skin effect under the interaction, and we name it the non-Hermitian skin cluster here. This talk consists of 3 parts. At first, I will brief the background of our research. Then I will discuss the main work. The final part is a summary. Now let me first introduce some background of our research. The non-Hermitian physics involves the study of non-equilibrium and the open system. It creates lots of new topological phases and novel phenomena. It also encourages the design of the corresponding experimental setup. But many works are in the non-interacting level, so I'm not going to talk about them today. And our research is focused on the non-Hermitian interacting system. Let me give an example of the interacting system. This is a famous example of non-Hermitian interacting system. The non-Hermicity comes from the of energy matrix. It will result in the well-known bulk Fermi arc. In this pictures, this is two quasi-particle bands, and they stick at the Fermi arc. However, many works focus on how to deal with this interacting model via the perturbation theory. So there is a question: shall we deal with this model in other ways? So our work might give a potential approach. And for this system, we don't want to deal with the interaction for that. It will not so easy to say the non-Hermitian effect via the perturbation theory. So we try to map this interacting system to an effective non-interacting system with a single particle hoping. And this is our motivation. And this is the Hilbert space graph for the 1D spin chain. And we can see the effect of the interaction is that they just connect some state in the Hilbert space. So if we label these links, then we can get a non-interacting model just with the hoping from one state to another state, not the hoping in the real physical space. So we design our model in this 4 terms of interactions. But why we prefer to use this form of interactions? Let's see, if we prepare a 2-particle cluster, just like this small packet in the pictures, under this interaction, it will drive this cluster from one side to another side. So here is similar to a single particle. That is the reason why we call it a cluster in our model. Now let's check the 2-particle model first. This is a Hilbert space graph. We can see this is just a 1D chain, and we can also label the amplitude of the links. And we found that for this model, it's just equivalent to so it's much more. We also plot the Hilbert space graph for the 3-particle model, and there is evidence Hilbert space fragmentation. We can also label this effective hopings, and for this 3-particle model, it becomes a 2D effective model, and then I will explain some details later. So on this basis, we can deal with our interacting non-Hermitian model in the effective model level, and we don't need to deal with the interaction. Now, before going to the main result, let me explain the non-Hermitian skin effect first. This is a simple model with non-reciprocal hoping, and the non-Hermitian skin effect can be seen under the PBC versus OBC. If the system is under OBC and the non-Hermitian skin effect works, and we can say there is skin localization at the boundary. We call it skin localization. This form of localization, skin localization. And for the 2-particle model, and we just it's just a 1D chain, the SH model. So when it's under OBC and there is asymmetric hoping, and we observe the skin localization as the physical boundary, but it's a localization of the cluster, not the particle. So we name this localization the non-Hermitian skin cluster. Now let's back to the effective model for the 3-particle. This is always a 3-particle effective model, and there is a physical boundary that like I put it here. And if we check the state in the Hilbert space, and we found that for some states the interaction only drives the single two particle cluster that I mentioned before, but it will touch another particles. If phase. And this is structure of the zero-mode state in the effective model. So in our model, there is not only the skin localization at the physical boundary, but also like at the interface. At first, let's check the localization at the physical boundary. The right figure is just one section of the localization at the physical boundary. Then there is also the localization at the interface. We found that these two types of localization are the same form. That's really interesting that the skin localization usually requires the physical boundary. It means the physical cutting off. But in our model, we found that the interface it's from the interactions. It can also host the skin localization, even if it's not a real boundary. So it will be interesting to check our model under PBC. This is the PBC lattice. There is no physical boundary, but the interface exists. And we know that under PBC it's difficult to see any other localization for that. The space is uniform, but in our model there is the interface. So of course we can say the localization. This is just one type of the PBC localization. The behavior is that this state is highly localized at the interface. Let's check the state, these highlight states. We found that this is this state in the physical space. We found that this is just some critical states that the two particle cluster is coming to touch another particle at the interface. So we name it the interface cluster in our model. And we can know that interface in our model can play a similar role to the real boundary. So the interface divide the PBC lattice into two areas, like I plot here. Of course, we can see other localization like this localized cluster and extending cluster, and we found that there is two bands of states in the complex spectrum, and we found that for the outer band states, those states localized in this neural area, so we name it localized cluster, and for the inner band, we name it extended cluster. And we know that the interface just somewhere that the two particle cluster touch another particle. So it will be reasonable to assume that for the outer band state, the interaction will induce the particle to get closer. So we can confirm this assumption by measuring this form of total on-site density for each eigenstate. And in this picture, this is density of the state of each eigenstate in the complex plane. And in this picture, there are two separate bands of states just like it in the complex energy plane. And we can see there is higher density for the outer band. So it just confirm our assumptions. Okay, this is all of our work. So we extend how the non-Hermitian skin effect works under the interactions. However, there are some works they talk about the non-Hermitian skin effect under the weak interactions, that they found that the property of the model will be sensitive to the boundary, but I think it's not a direct approach. But in our model, the behavior of the skin effect is that we found the localization of the cluster in the effective space, not the physical space. So I think this portion is much more easier effect for interacting system. Then I'd like to introduce some potential relation between our model and the many-body localization. That I think our model can be a candidate platform for the many-body localization. What I'd like to mention is that there are some research that focus on the disorder in the non-Hermitian system, but they just use symmetric hopping and this on-site gain and loss. They found there is many-body localization from the weak disorder to strong disorder, and this localization can be seen from the entanglement entropy from the volume law to the area law. But the origin of our model is different. This is the Hilbert space fragmentation, and it doesn't require the disorder. This is an example of the Hilbert space graph of our previous model with 4 particles, and we can see there are 4 disconnected parts. So I think it will be interesting to study the many-body localization in such a non-Hermitian interacting system. And this is all of my work today. I'd like to thank my supervisor and other members in this group for their help in the research. At the end, thanks to everyone here. Okay.
Okay, thank you very much.
Okay, thank you.
Yeah, so we're open to questions.
Okay.
Questions from the audience?
Hi, can I ask? Okay,
yes,
can
please.
come, right? Yeah, so the thing is just like, so you need this asymmetric hopping to see this non-Hermitian scaling effect, right? Is that correct?
No,
or is it possible
sure.
even with a symmetric kind of hoppings, you still can have that?
You mean? Yeah. This interface comes from the symmetry hopping. Yeah.
Okay. I mean, again, I think my question is, in a sense, how this interface is actually appears here. Is it something construction or?
It's from the particle symmetry that we know it's the Boson model, and we can switch the 2 particles in the Hilbert space, so there will be an interface.
Okay. Yeah. So and okay, if I am able to let's say allowed to make a comment, like the one that you are saying, you mentioned that this MBL, yes, people do most of the time represent in the so-called real space or the physical space, but there is also a phase-space analogy of way to understand also this so-called this ETS to MBL kind of transition. So it's not only for so-called non-Hermitian system, even for Hermitian systems, I think phase-space.
Sure.
Thanks.
Yeah. Thanks.
Good. Any other questions? Maybe can you also show the slide of the Hamiltonian in related to the previous question? So the Hamiltonian you're trying to solve for this interesting interface behavior. Okay. So this is really a purely interacting system.
Yes.
Okay. So is the main message also proposing a new type of skin effect with periodic boundary condition?
No, actually it's not a new type of skin effect. It's just we also measure it in terms of localization, and we found it's not the localization of the single particle. It's the localization of a group of particles. So it's just the different behavior of the particle, not the different skin effect, I think.
So it is this kind of localization of a cluster of particles.
Yeah.
Is it still possible with a single particle Hamiltonian, or do you always need to have interaction for this to happen?
But for our setup, it requires this pure interaction.
I see. That's great.
Yeah.
Okay. Any other questions? If not, let's thank the speaker and move on.
Let me stop.
Okay, thank you. So our next speaker is actually Sun Hao from my group. Okay, Sun Hao, when you're ready, please share your screen.
Okay.
Yeah.
Can you see my screen?
Yes. Can you go back to the first slide?
Okay.
This is the last slide, is it?
Yeah, it's first slide.
Okay. All right, you can start now.
Okay. Hello, everyone. My name is Sun Hao, a research fellow in NTU. I'm very glad that I can have the opportunity to introduce my work. This is the title of my presentation. And if you want to know more about the detail, you can check this paper. So, sorry. At the beginning, I would like to thank my co-supervisor, Professor Sangupta, and Professor Yang, and also my previous supervisor, Professor Nang, and also the funding agencies. So before the main text, before the main talk, I would like to illustrate my motivations. So my motivations come from three aspects. As we know, the topological phases of the boson of collective excitation have been steadily gained interests. But there's still some problem, especially for the experiments. As we know that, for example, when the thermal Hall, the triplon thermal Hall effect actually has a problem for this non-trivial transport is still not observed. And which require us to provide more theoretical predictions or to study the interplay between the measurement and interplay between the band and the magnetic field. For the second part, for the second one is for the band engineering itself. We want to provide more simple model with non-trivial geometry or topology, which can provide a more provide insight of this band engineering. And the third one is actually for the more complicated cases. So this is the correlated states, because we know that in the zoo of the correlated states, a lot of novel quantum states with non-trivial topology can be hidden in this. So this is our motivations. So basically, this talk has three parts. The first part is the background and introductions. The second one is I'm going to talk about the results and discussions. And in the last of the discussions, I'm going to talk about some outlooks. And the third part is a conclusion, some remarks. Okay. So now let's start the background and the introduction. So my the explicit system what I studied actually is focusing on this SS model. So basically, the SS model is a paradigmatic model for the frustrated quantum magnets. As you can see that in this model, in this latest model, it contains two dimers in the unit cell, as shown in the translucent ellipse, dimer A and dimer B. For the prototype material in the real world is a strontium copper borate, and which has the strongly interacting layers, and with a dimer of copper atom with spin half with half spins. Basically, this spin dimer in this materials can hold a single letter ground state and also excited triplet states. This energy spectrum is already verified by both experimental and also experiments and theory. Basically, these excited triplet states can form a band structure. Means it can form a band structure which called a triplet band. And in this typical SS model, it has a two dispersive band and one flat band in the middle. Okay. So, okay. Mathematically, we describe this SS model by this spin Hamiltonian. We consider about the exchange constant and also the diamond interactions with different different distance, and basically a very popular way to solve this Hamiltonian is basically to use a bound operator formalism. We can transfer this spin Hamiltonian into a effective Taliban Hamiltonian. So the spin dimer model can be simplified into a lattice model, which we discussed in this paper several years ago. So, okay, previously, by using this simple lattice model, the researcher found that this triplon excitation can hold a topological phase transitions at a weak magnetic field regime, which means that at this spin 1 Dirac cone, it can be gapped by this small vertical magnetic field, and then can hold a non-trivial or can hold the gapless edge states, which can contribute to the thermal Hall conductance or conductivity. So as what I said in the motivations, this triplan thermal Hall effect is still not observed in experiments, and also for the which means we have to provide a more discernible signals to help the experiments. And for the model itself, as we know that I think since it contains 2 dimers, but this single dimerless model is too simple. Actually, it's too simple to capture the nature of the triplan excitation. So based on these questions, we developed our own theory, and I'm going to show it in the following. So so we started from the 2 dimer lattice model, and we started this more general cases. We start from the 2 dimer models and put the model into the 2D magnetic field with both in-plane component and also the out-of-plane components. Basically, the Hamiltonian of this system can be written in this way. It can has a more comparable form. So here we include the sublattice 2 spin for these 2 sublattice into this model, and the matrix M now is this is the this is a this is this is interdimer hopping, and the matrix N described as the intradimer energy and the hoppings. So with this Hamiltonian, we find that for the lowest 2 bands, it can hold a path flux. It can hold Dirac points. So by studying this field effect, we can see that, for example, if we have an out-of-plane component, the magnetic field, the band can be split. However, if we have an in-plane magnetic field, we can shift the band and can create a Dirac point here. If we have 2 components, we have both. Actually, this Dirac point can be gapped. And we also show the 3D maps and the contour of the band. We can see that high anisotropic of this band structure. This is induced by the in-plane magnetic field. So in order to understand well this band behavior or band geometry, we build an effective Hamiltonian, and we can see that the in-plane magnetic field acts as the in-plane magnetic field couples the pseudo-spin freedom and the momentum, and give rise to a Rashba spin-orbital coupling like Hamiltonian. And the out-of-plane magnetic field actually acts as a Zeeman field. They can split the band. So basically, this in-plane magnetic field induced the Rashba spin-orbital coupling contributes to the Dirac points. As we know that the novel property can happen in the Dirac point, so we started the property around this Dirac point. We from the Baire curvature calculation around this point, we find that the phase is about pi, which can hold and means the out-of-plane magnetic field. We can create a gap here, and then we can have a non-zero Baire curvature distribution. And from the thermal Hall conductance calculation, we showed that we could know that this induced Baire curvature hotspot can contribute to thermal Hall conductance, which means that this thermal Hall conductance can be different if we apply the in-plane magnetic field. So in order to verify this, we calculated the signal for the experiments, we calculated the thermal Hall conductivity, and so we can see that clear signal that when increase the implant component of magnetic field or increase the tilted angle, for this part, the positive thermal Hall conductance can go through 0 and to the negative region. And then this can be understood by this Berry curvature distribution. Basically, the positive value of this Hall conductivity is contributed by the triplan localized at an endpoint, which holds a positive Berry curvature. However, this negative value of the Hall conductance is dominated by the Berry curvature hotspot at the gamma point. This is a Berry curvature hotspot is induced by the implant magnetic field. From the calculation, we also show that this kind of negative thermal Hall signal is linear proportional to the diameter interactions, which means that the diameter with large diameter interactions, we can have a large negative thermal Hall conductance. So basically, we see that the implant magnetic field can induce the negative thermal Hall conductance, which provide a possibility of tunable the tunable non-trivial thermal Hall transport. This is those are some conclusions. So later we consider about a more realistic way to control to achieve these tunabilities. We consider about the optical amplifications, and basically this optical amplification described by this Hamiltonian. We can see that by absorbing a photon, actually we can create a pair of a megaton or triplan with opposite momentum. And from the Hamiltonian, we can have the dynamical frequency of this time evolution of the triplan amplitude. And once we have this simple resonance condition matched, means that the energy of the two triplan matched the energy of the external light, we can have resonance, and then we can have a triplan. We can have exponential growth of the triplan density, and also the very interesting thing is we also find that because the band energy of the gamma and M are different, so the resonance frequencies are different, which means that we can use different frequency to excite electron. The triplan localized at a gamma point or M point. And because we know that at a gamma point, we have a negative Berry curvature, which actually can contribute to the negative thermal Hall conductance. And we can, basically we can generate the thermal Hall flow as shown in this red curves to the left. If we use a light about 1.4 terahertz, we can excite a triplan at the endpoint. And because at the endpoint we have a positive Berry curvature, and we can get the positive and negative positive thermal Hall conductance, and we can generate the Hall flow to the right. That means we can selectively amplify the triplan density at different key points by this resonance conditions, or by choosing the different external light frequency. So this basically provides us a very reliable way to achieve this tunability. Okay, basically I introduced what I did. So actually we can do more. Here is some tool actually to the project what I'm doing now. I turn to some other interactions, and also the pseudo spin freedom with these two values. And we may also apply the string engineering to change the band geometry, and we can fulfill this triplan dynamics. This is the method what I apply. I basically employ the optical block equation. This is a very efficient way to study these megaton dynamics or triplan dynamics in a very short time scale. So another one is is about the interacting meganons. Basically, we know that a spin system is strongly interacted. So the interaction is ubiquitous. So the full picture of the magnon is basically the interaction is very the interaction effect is very important. So basically, the goal is I'm going to study the role of the diamond interaction. So this basically this is a symbol or a single particle interaction, single particle terms, and with the interaction, so there could be a different results of this this system, and also the boundary normalization by the interaction, which couples the topology, will also have a very plenty physics, plenty of physics. And the second, the third one is. Okay. So I
one more slide. Yeah, this is just some
finish.
outlook, right?
Yeah. So I can stop here. This is some conclusion remark. Okay.
Yeah, I don't think we have time for questions. We are already 2 minutes over. Now, quick comment is maybe Arpit, and you can talk, because the 3 ingredients I mentioned about Arpit's working injection current, we all have this here in this magnon system, right? It's a bosonics.
Yeah, right. Yeah.
Maybe something interesting can happen.
Yeah, the method could be the same. And
indeed, I was also thinking exactly the same thing.
Yeah.
So,
yeah. And everyone,
would you explain exactly what you were thinking? Do you mean there's an injection current of magnons, or would you?
Yeah,
explain?
something like that. We do have very narrow bandwidth here. We also have a very curvature dipole, and definitely we can break the symmetry, for example, by in-plane magnetic field or strain.
Yes, but then your flat bands are flat bands of magnons, right?
Yeah. So it's a boson. It's a bosonic system.
Yeah, but then so it's a bosonic system that I'm not sure how you define injection currents of a bosonic system.
It's a spin current, probably.
Yeah.
You can
okay, let's talk.
Yeah,
It's not super clear to me that okay. Mm-hmm. Yeah. So you're thinking of injection currents of magnons.
Yeah, exactly.
Right.
Yes.
Okay,
yes.
fine. Yeah.
Okay, yeah, thank you. So again, feel free to message Sun Hao privately or using the Zoom. We don't have time for question now. Okay, let's move on to the next speaker is Dima from Pinaki's group. Okay, so Dima, if you share your screen. Okay, you can start.
Okay.
Mm-hmm.
Good afternoon, everyone. I am Dhiman Bhomik, and today I am going to talk about this study, which is about twisted superfluid and supersolid phases in bilayer honeycomb magnets, which I have done with the collaborator Abhinava Chatterjee and Professor K. Pranigrahi and Professor Pinaki. So here is my outline. First, I'll give a general background to everyone who does not know or familiar with the superfluid or super solid. Then I'll go into depth into the model of what is the spin Hamiltonian and how I come to the triplet Hamiltonian. And at the end, I'll show the results of that model. So first, the general background. So what is a superfluid? Superfluid is a state of matter where all the bosons in the system condensate at a particular energy level, which is similar to the superconductor and Bose-Einstein condensate. And superfluid phase has an order parameter, which is a macroscopic wave function. That is a square root of the number of particles multiplied by e to the power I times the phase. And the phase and the number of particles can be spatially and varying or temporally varying. So what is normal superfluid? Generally, superfluid denotes this normal superfluid where the number of particles is constant throughout the space and time, and phase is also constant throughout the phase and time. So here is a schematic picture of that totally uniform superfluid. And what is twisted superfluid? In case of twisted superfluid, we have the number of particles which is constant over the space, but the phase is varying over the space. So here the pink area have different phase phi2 and the blue area have different phase phi1. And along with these phases, we also can have booster of superfluid and a normal solid, normal fluid phase similar to vortices in superconductor, which have a constant phase and zero superfluid and non-zero superfluid in other region. So here the spin model which we have considered, where we have considered a bilayer honeycomb lattice, where we have considered A stacking of the honeycomb lattice. So due to this A stacking, the first term denotes a Heisenberg exchange interaction, which is in between directly the interlayer bond. And we also have the magnetic field perpendicular to the lattice in the Z direction. And the third term denotes the Heisenberg exchange interaction on the nearest neighbor bonds, which is denoted by the red line here. And the last term is the DM interaction, which is symmetry allowed, and which is on the next nearest neighbor bond, which is denoted by this red and the green lines. So what is the ground state of this Hamiltonian? So we are considering a limit where the J perpendicular, which is the Heisenberg interaction of in the interlayer bond, is very high compared with the Heisenberg interaction intralayer on the interlayer bonds. So in this case, we have a ground state, which is a product state of singlets, and singlets are on this interlayer bonds. And the excited states are triply degenerate, which is known as triplet. And throughout this study, we use the term triplon, which correspond to the quasi-particle triplet of the excitations. So about the ground state and the quasi-particle excitations triplet, what about the excitation, how they vary with the magnetic field? So if we have at zero magnetic field, we have the ground state of singlets and exciteds, which are triply degenerate, which I have shown schematically here. And if we apply the magnetic field, the three triplet energy level splits out. And out of the three triplets, two of them is highly separated compared with the ground state, and the triplet, which is directed towards the magnetic field, becomes similar to the energy with the singlet at finite magnetic field. And after this cutoff of the magnetic field, we have triplet as a condensate. So to describe the system, we can consider these two quasi-particles. One is singlet, another is a triplet. And for more simplicity, we consider singlet as a vacuum state, which means that if triplet is not there, it means there is a vacuum, and that denotes the singlet. And that can be done using the bond operator formalism, where the spin operators are transformed in terms of the triplet or triplon operator, where this T operator denotes the annihilation and creation operator of this triplon. And so after this bond operator transformation, the Hamiltonian is of the following form. So it is noticeable that after we transform the Hamiltonian in terms of triplon, it becomes a from bilayer system to single layer system of the triplon, because the triplen reside on the interlayer bonds, and it becomes a Hamiltonian of triplon on a single layer honeycomb lattice. And further noticeable is that this first two term denotes the Halden model, where the first term is the real hopping on the nearest neighbor honeycomb lattice, and the second term denotes the complex hopping on the next nearest neighbor bond. And this term is the on-site potential of the triplons, and third term is the repulsion of among the triplons. As we increase the magnetic field, you can see that we populate the lattice with the triplons. And in the non-interacting region, where we neglect the last term, repulsion, we can explore this system using the exact diagonalization by having band structure. And after diagonalizing the system and having the band structure, we get these two types of band structure in two different limit of the DM interaction. When the DM interaction is very small, when it is below this value, then we have the minima point is a gamma point. And when DM interaction is very high and it is greater than this value, the minima point is at the K point. And that is the main reason we have the twisted superfluid because in this regime. So we get normal superfluid at the when the system is condensated at gamma point, but we get a twisted superfluid when the Bose-Einstein condensation happen at the K and K prime point. And when in this limit, system chooses either K point or K prime point based on spontaneous symmetry breaking. It is quantum disorder by order phenomena. And in presence of interaction, we'll see that we also get twisted super solid phase. And to study the system in presence of the interaction, we used Cluster-Cruzier mean field theory, where we have the mean field regime along the vertical direction, which is denoted by the blue region, and we have the periodic boundary condition along the horizontal direction, where which is denoted by the pink region. And the system is denoted by this black boundary, dotted boundary, where we have 18 sites, and we have 3 different kinds of sites in the lattice, and we have sites without any boundary effect. So we use the algorithm in the following way. At first, we diagonalize the Hamiltonian with the mixed boundary condition because we have mean field along this direction and we have periodic boundary condition along this direction. And after diagonalizing this, we determine the mean fields within this blue dotted box, and then we use this mean field again in the second iteration, and we finish the iteration until the result converges, or mean field parameter converges to one value. And after doing this, we get the following results. So here I have plotted 4 results where the number A. So you can see that in the horizontal direction, this is the result where the DMI is increasing, or in terms of Haldane model, the complex next nearest neighbor is increasing. And in the vertical direction, the interaction is increasing among the triplons, the repulsive interaction. And so let's start with the plot A, where it is well-known plot in the non-interacting limit, where the interaction is small. So first, the magnetic field increasing. So at 0 magnetic field, the lattice is empty of triplons. So there is no triplon. And at a cutoff of the magnetic field, the number of triplon rises, which is denoted by this black line, which denotes the number of triplon. And after a finite magnetic field, the number of triplon per site is 1 at every site. So it's saturated. All sites are completely filled. And in between these 2 regimes, where empty and fully occupied, we have a superfluid phase, because this red line denotes the superfluid order parameter, which I had discussed before. And this is not a twisted superfluid because the phase is uniform throughout the system. And if we increase further the DMI and above a cutoff, we get the following phase diagram, where we have a twisted superfluid in place of superfluid. Which is it is a similar phase diagram with the A, but in place of superfluid, we get a twisted superfluid because this green line denotes the difference between the phase of the superfluid order parameter on the next nearest neighbor bonds. And as we increase the interaction among the triplons, we get the following phase diagram. So you can see, you can compare the phase diagram with respect to A, and you can see that there are still superfluid phase, but in between 2 superfluid region, we have a charge density wave region at half filling of triplon. So as we increase the magnetic field, at half filling, we get a charge density wave because this is the charge density wave order parameter, which denotes the difference between the number of particles within the nearest neighbor bonds. And this superfluid is still normal superfluid because the DMI is low and we have normal superfluid. And as we increase the DMI, in place of superfluid, we get twisted supersolid. So in case of twisted supersolid, we don't have uniformly distributed superfluid. So the number of particles is different at different sites, which is we can see in the charge density wave order parameter. And we have also superfluid, non-zero superfluid order parameter in this region. And yeah, from this we get this behavior. And here is the phase diagram from the combining the whole picture. And here is a phase diagram. So at low interaction, we get superfluid, and at for smaller DMI, and for high, so for low interaction at higher DMI, we get a twisted superfluid. And as we increase the interaction, we can compare this phase diagram A and phase diagram B. We can see that we get a charge density wave in between two regions. So charge density wave separates the regime of superfluids, and it also separates the regime of twisted superfluid. But at high interaction, in place of twisted superfluid, we get a twisted supersolid. So that is the final result. Thanks for your attention.
Okay, thank you. Yeah, we have time for maybe one or two quick questions.
Hi, Demon. I have a question. So,
Yeah.
so you define an effective single-layered Hamiltonian for your triplons. So,
Yeah, correct.
So I would like to get some clarification about definition of twisted superfluid and normal superfluid.
Okay.
Yes.
Oh, I see. So in case of twisted normal superfluid, so I had the schematic here, which shows that so we can define a superfluid using the macroscopic wave function, which is called the superfluid order parameter, which contains the square root of the number of particles and e to the power I phase. So in case of normal superfluid, the phase is constant throughout the material, whereas in case of twisted superfluid, the phase is not constant. So some regime, the phi1 is here and phi2 is different. So the phase is not constant. So in our case, the phase diagram, you can see that I have plotted along with the magnitude of the superfluid order parameter, the phase. So this is the phase difference between the next nearest neighbor sites. In case of normal superfluid, there is no phase difference, and non-zero superfluid magnitude of the superfluid order parameter, and this is also non-zero magnitude of the superfluid order parameter. But the phase there exists a phase difference of the phase of the superfluid in the lattice.
I see. Thank you.
Yeah.
Okay, yeah. So maybe a quick question is: so for the twisted superfluid, you have a current, supercurrent in the ground state. Is that right? Is that the experimental significance in distinguishing between the two?
No, I cannot tell there is a supercurrent because it can have a local current because there is a time
local current. Yeah.
Yeah, it might have local current, but I have not calculated yet.
The current related to the gradient of the phase as well?
Yeah, it should be like that.
Because then if you have a difference in phase, you have a current at the interface, right?
Yeah, it should be like that. It should have current at the interface.
Okay. Okay, great. Thank you. Let's move on in the interest of time. So our next speaker is Amdad from Marcos Group.
Yeah, hi, hello.
Hi. Yeah. You can share your screen and you can start.
So can you see my screen now?
Yes, you can start.
So hi everyone. So it seems like so my presentation is a bit different than what I was listening for some time. So what I'm going to
are you in the presentation mode, or
yeah,
we can only see your slide in the unpresented mode.
So
okay, you can start. You can. Oh, you're not going to use the presentation mode.
oh, I see. Slideshow. Sorry. Is it okay?
Yes.
All right. Sorry. Yeah. So yeah, I'm going to talk about some type of OIB structure. I mean, OIB phenomena. I mean, so the title of my presentation is Solitons and Rogue Waves in Optics. So I'm going to talk about three types of solution of a, sorry. My slide is not changing.
Yeah, maybe you exit the presentation mode. It all depends on which window you are sharing. If you are sharing the screen, the desktop. That's probably the easiest. If present with this mode, it's also fine. You can just press page down to the next slide.
So this one.
No, we are now seeing. Okay.
Right.
Okay.
So I can go in this way.
Yeah, you can go in this one. Oh,
okay,
great.
so I think now it's working.
Yeah.
So I will be talking about some OIB solution. So three localized solution. It's called solitons, breathers, and rogue waves. So these are the structure of a solution of a partial differential equation, which we call the nonlinear Schrodinger equation. So the equation is look like, I mean, this, and I will be talking about this equation a bit later, but the focus will be mainly talking about these three solutions. So these solutions usually happen in optics, as a solution of this equation. So I will go one by one and basically talking about their main. What is the, I start with soliton, so it's look like this. So this is I'm not sure if you familiar with solitons and nonlinear waves. So, but these solitons, I mean, if a medium, especially in optical fiber, it has a nonlinear properties and it has the dispersive properties. Usually the dispersive property try to spread the wave, whereas nonlinear property try to hold the wave. But when they are in a balancing mode, then the wave propagate without any change. So, and it's called soliton, and it is a stable form of wave. So the balancing act of dispersion and nonlinearity give rise to this kind of wave structure, and it will propagate without any change of its shape. So their application has like data transmission or signal processing, generating new frequencies. I mean, it has a lots of application. So, I mean, these are the few that I mentioned here. And so it has a bit of a history. I mean, it's like 1834 in the year. Some Scottish naval engineer first observed this kind of wave in water. So in a canal, I mean, this is a recreation of what he did. So he was actually dragging a boat along a canal, and what suddenly he noticed is that a heap of wave was developing in in the front of the canal, and it was moving without any change of the shape. So this is just a picture, that they are trying to recreate what he observed. As you can see, there is heaps of wave. It's moving along the canal, and some people are curiously observing this. So this is the first observation of this kind of wave. And of course, later it has been observed in optics, and there was a lot of studies, and then people try to apply in a various way in optics. So I mean, to give a bit of a more background on this wave, its mathematical form is sec h square. The solution is mostly this, and it's do not change profile along the propagation. So this is the fundamental solution of the NLSE, means non-linear Schrodinger equation. So this is the solution of this equation. So, and this is the first order solution. And the higher order solution is the non-superposition of the first order, so which look like this. If two of these fundamental types solution move together, so they periodically move along the propagation. And they are like compression and relaxation in this way. They are moving forward. So I'm just, I make a bit of a simulation. This is the first order solution. So at this moment, Z is the direction of propagation. It's propagating along the time. As you can see, it's not changing its shape when it is propagating. This is the twice pi propagation, I mean, along the evolution. And here is the superposition. I mean, this is called second order solid solution, and it moves periodically. So it's like a bit compression and decompression and compression again. So it moves periodically like this way. And this is the third order. I mean, 3 soliton is moving along the propagation direction in time. So it will propagate in this way. In the right side, you are seeing the exact same thing, but in a 2-dimensional picture. So this is also twice pi period. It's a periodic motion. So that's how they move with time. So these are the previous slide. I mean, these are the bound structure, very symmetric, very regular and coherent structure. In reality, in any optical fiber, I mean, if we can keep the optical properties of the medium in a way that it can sustain this, bound structure, that it will definitely move in this way, the very regular and periodic motion. However, in a real optical fiber, there are lots of other nonlinear or linear effects exist, like Raman effect, self-steepening effect, higher order dispersion effect. This is the realistic scenario. And in that case, when a soliton is launched into a fiber, in the left side, the picture is, at the beginning, it is a soliton, higher order soliton, like third order or fourth order soliton. But when they face all the non-linear and non-linear effect in optical fiber, it just immediately breaks apart. So in the right side is its frequency domain. As you can see, the soliton breaks apart and it just, it is developed as a continuum, and we can see there is a continuum of frequency is developed when it's evolving time. And frankly, I mean, in a real world application, so there is a range of frequency we can generate using this soliton in the optical fiber, and those frequency can be used for data transmission or in medical application. I mean, there is a whole range of application that we can use with this new frequency that has been generated in a real optical fiber using soliton. So this is the part of the soliton. So now this is the breathers. So this is a different type of waves, but this is the same solution of the same equation, which is nonlinear Schrodinger equation, but it's a bit different. As you can see, it is a periodic structure, and it's developed on a constant of optical or hydrodynamics field. I mean, this kind of wave can be found also in hydrodynamics as well. So this is called breather. So, or sometimes people call it a train of pulse. And unlike soliton, this pulse emerges from I mean, usually the unstable property of the medium simultaneously grows this kind of wave. So now I'm going to talk about the physical mechanism, the fundamental mechanism that actually give rise to this kind of wave in an optical medium. So, and it has a frequency com, which is used for a very narrow band frequency to measure very minute detail optical metrology. I mean, for very accurate measurement of frequency, this kind of frequency comb is used, and also to control the noise in optical system. So what is the mechanism? As you can see in this picture, from the left, this is a carrier wave. So this is a carrier wave, and which has a single frequency. And if a little bit part of this carrier wave, we can see there is a slight modulation is developed on the carrier, and the carrier eventually grows into a train of pulses like this. So that's how instability and give rise to a series of pulses. So this kind of phenomena in a real world, in a natural scenario, you can see in a desert, in a sand dunes, you can see this kind of pattern formation. So this pattern formation actually is a manifestation of a modulation in stability. These are the A is the soil formation in a cool down lava. So they produce some kind of pattern, and B is an incoherent light, and C is a coherent light. So we also pattern formation, which actually, as a result of the modulation and stability, some grass formation, and these are the some pattern in E and F. F is the pattern in some kind of animal skin. So I mean, the modulation and stability actually give rise to this kind of pattern in a real world scenario. I mean, these are some example of this. So to go a bit more deeper into the mechanism, how they work. So if you look at the beginning, the red arrow, this is a planar background, and it has been modulated with a two very small modulation, which will give rise to the central compressed and periodic train of pulse in the middle. And then it goes to the background again. The modulation and the amplitude goes to the background again. So this is the temporal, I mean, in time domain or time behavior of the solution. But if you look in the frequency domain, what happened is, so as you can see, the carrier, it's a single frequency carrier, and we modulate this carrier with two sidebands, two very small frequencies. So the carrier energy goes into this carrier. From the carrier, energy goes into this side frequency, and gradually these small modulation frequency create more frequency component with their harmonics, and it grows like this. The harmonics are new frequency is generating, and energy is going from carrier to the sidebands, and And when all of the energy from the carrier goes to the sideband, we get in the middle, the compressed part. And this is the maximum growth happened here. And then finally it goes to the carrier. So cascade also developed and then goes to the background again. The amplitude goes to the background again. So this is it's called a first order solution.
Running out of time.
Yeah. Sorry. How much time do I have?
Negative 15 seconds. So can you just go to the summary page maybe, or just wrap up quickly within 1 minute?
Yeah. Right. So 1 minute. Okay. So this is the breather, and this is the second order breather. And sorry. So I will skip a bit of detail. This is the rogue waves. I talked about breather, this rogue wave. It's actually connected with one period of a breather is, I'm just showing you how the rogue wave emerges. So when the period of a breather, we have a rogue wave in the middle. I mean, there are lots of fundamental mechanisms going on. Very high intensity optical pulse can be found in optics. This is optical rogue waves. So this is a higher order optical rogue waves, second order, and this is a nonlinear superposition of 3 first order one. So this is a fifth order rogue wave, and if we break apart them, we can get a cluster of rogue waves. And in a real world scenario, in a chaotic wave background, in a numerical simulation, we can see that this kind of localized formation we can observe in a realistic scenario. So the final point is in here. So this is an equation of a realistic, to simulate a realistic, optical fiber simulation. We have a Raman effect, we have a self-steepening effect, and various other effects. And those effects combinedly grows into this kind of, evolution and this kind of optical spectrum. So this is the soliton based. The question is, can we get the similar type of things using the rogue wave? I mean, primarily there is a similar type of continuum using the rogue wave in an optical fiber, and this is a very recent development. That's
okay.
all.
Great, thank you. It's actually very interesting, but we're really running out of time. So
Sure, no problem.
if there's any question, just you can message.
Yeah, sure.
Okay, great. Thank you. Let's move on to Wang Zisheng from Professor Feng Yuanping's group.
Okay.
Great. Yes.
Yeah.
Yeah, you can start.
Thanks. Okay. Good afternoon, everyone. This is Wang Zisheng from Professor Feng's group. Today I'm talking about the comfortable transitions between mutable transient waves in monolinear 1T/s2. Here is the structure of this talk. First, we began with the electronic properties of PMDS, especially about the CDW properties of 5D group PMDS, then discussing the mutable CDW structures of VSE2 with its potential mechanism. In the second part, I will show results about the VSE2 CDW transitions under the doping and the influence strand, and the qualitative explanation will be given based on the potential mechanism. In the third part, the order loop is given, which can make the analysis from the qualitative to quantitative. So let's enter the first part. PMDS have received wide research interest due to their various properties, such as superconducting and topology. Among them, CDW have been widely observed, and the distorted structure of T prime and T double prime phase can also be regarded as CDWs. Besides, CDW can coexist or compete with other normal properties which make CDW deserve further studies. In this work, we focus on the 5D group transition metal diacyanates. Generally, I mean, NBS2 or TASE2, their T phases have the implant root 13 by root 13 CDW structures with motor transition, and their atrophysis have implant 3 by 3 CDW structure with entropic CDW gaps. Due to the layered structure of the TMDF, their bulk and monolinear counterparts have same implant lattice distortions. However, things become interesting when it comes to the from a CDW case. It is known that the bulk VS2 has implant 4x4 CDW structure. However, with the decrease of layer thickness, different CDW patterns have been observed, such as 4x3 for multilayer VS2 and the root 7x3 for monolinear VS2. So as mentioned before, a different CDW symmetry between the bulk and the monolinear VS2 is unexpected. Such phenomena may indicate that the CDW properties of VS2 are sensitive to the external stimuli, and we focus on the monolinear VS2. At the high temperature, the pulse results agree well with the DFT band structure. An electron pocket and M point and 3 bands are near converged at the gamma point. However, below the CW transition temperature, an energy gap will open at the MK path, while there is no obvious change around the gamma point. So this is a partial gap opening at the Fermi level. And such phenomena can be understood by a theoretical model called Fermi substance listing. Here I use one dimensional metal with lattice constant A as an example. Suppose this is a half-field band, so at the ground state, the electron will fill up to epsilon F. However, if we consider the electron interaction, this energetic field we introduce a periodic lattice distortion with period lambda defined by this formula. The 2kF is a so-called listing vectors. So in this case, lambda is 2a. Since the lattice has been doubled in real space, a new gap will open at the epsilon F, which alone some electrons spill down, thus lowering total energy. This is the case for one dimension. For 2 or 3 dimensional cases, a favorable thin surface geometry is necessary, and such listening will mostly like occur when the shape of thin surface permits the connection by the same listening vectors. So let's take a look at the monolinear VS2 frame surface. The left graph is obtained by integrating a pulse intensity around the Fermi level, and the right graph is obtained by DFT calculation, and they are agree well with each other. Notice that the too long age of the electron pockets are nearly parallel, which gives a greater listing foundation to form a CDW distortion. And a lot of literature from both theoretical and experimental parts all suggest that thin surface listing as the driving force of CDW distortion in the monolinear VS2. The second part, I will show our results by using force principle calculations. Here I show the photon dispersion curve of monolinear based in VS2. Two imaginary points are shown in the graph, which indicated that the structure is unstable. The CDW distortion may arise spontaneously at the low temperature. The imaginary point at the middle of gamma and gamma Q1 corresponds to the 4x4 CDW structure, while another imaginary point at the gamma K path, gamma Q3 plus a current nominal Q2 at the M K path corresponds to the root 7 by root 3 CDW structures. So according to the formal spectra, both the 4x4 and the root 7 by root 3 CDW are possible. However, the calculation results show that root 7 by root 3 CW has lower energy, which explains the most observed pattern in the experiments. To understand the underlying physics, thin surfaces are also calculated. As mentioned before, the electron pocket gives the greater listing condition for all 3 CDW vectors. And the thin surface listing can be understood quantitatively by these two formulas. The first one is called the imaginary part of the electronic supportability. It is an integration of two data functions in the first Boolean room, and it is a direct measurement of the thin surface listing. Another one is called the real part of the electronic supportability. It is also an integration in the first Boolean room with F is the Dirac function, and its deep indicates the electronic stability. As shown in the graph, it's clear that the local extremes of the box imaginary part and the real part electrons, they are very close to the CW vectors, which supports the thin surface listing understanding. So let's take a look at the VSD2 under the external factors. First, let's take a look at the doping effects. Here I show the funnel dispersion curves under the electrodoping and the whole doping. For clarity, I only show acoustic funnel models when doping concentration above 0.1 sites per formula unit. As you can see, the electron doping doesn't have much influence to the funnel dispersion curve. Such slight shift of dips can be understood by the increase of Fermi level, which is similar to a so-called two-tap effect implies strong incandescence. On the other hand, for the hot doping, previous deep Q1, Q2, and Q3 have been surprised, while the new measurement point appear at the M and the middle of gamma K point, named Q4 and Q5 correspond to the new 3/√3 CDW structure. So according to the funnel spectrum, it is expected that the new 3/√3 CDW may appear under the hot doping. To further explore the possible CDW phase transitions, here we define the CDW formation energy by these formulas. ECW is the total energy of the VA2 CDW structure. X is the number of formula units in this structure, and E naught is the energy of the number 1/1 phase. Based on these definitions, here I show the CDW formation energies calculated as a function of the doping concentration. Two possible phase transitions are shown in the graph. The ground state of VSD2 may change from √7/√3 to 4/4 with the doping concentration around 0.23 electrons per formula unit, while for the whole doping case, as created by the funnel spectrum, both 4/4 and √7/√3 CDW have been surprised, while the new 3/√3 CDW has lowest energy. To understand the underlying physics, here I show the Fermi surface of VSD2 under 0.3 electrons per formula unit doping concentration. Due to the increase of Fermi surface, previous electron pocket at the M point evolve into the triangular hole pocket at the key point, and the Q1 corresponds to 4/4 CDW structure, much in condition now, while the Newton condition for Q2 and Q3 correspond to √7/√3 CDW structure nearly broken. So the three terms spend more energy to lock into the lattice for the √7/√3 CDW, and this gave the explanation why the 4/4 CDW has lowest energy at this electron doping concentration. This is the Fermi surface under the hole doping, and the decrease of Fermi surface shrinks the electron pocket at the M point, which breaks the Newton condition for Q1, Q2, and Q3. However, a new CDW vector, the Q5, match Newton condition now, which explains why the new 3/√3 CDW has lowest energy at this high hole doping concentration. Next, I show the funnel dispersion curves on the different impedance strengths. Again, for clarity, I only show acoustic funnel models for large difference. I show the increase of comparison strengths. For the imaginary model at the gamma M and gamma K has become deeper, and then additional imaginary point appear near Q6, which is one of the 4/√3 CDW vector. Such phenomena may indicate a more complicated computation among 3 CDW phases, 4/4 √7/√3 and 4/√3 CDW in the mononuclear to under the competitive stress. While for the tungsten, a wide and deep dips appear along the high symmetry path, which indicates the structure is very unstable on the large tensor strength. The CDW formation energies are also calculated as a function of the strength. And this time, very small, around 1% of competitive strength can induce phase transition from √7/√3 to 4/4. And I also show the Fermi surface of VSD2 on the 6% competitive strength. And similar to the electron doping case, there are 6 near triangular hole pocket at the key point, and it is trying to find that such Fermi surface topology can support all CDW vectors, Q1 for 4/4, Q2 plus Q3 for √7/√3, and Q6 for 4/√3. And this is the Fermi surface of VSD2 under the tensor trend. As you can see, the Newton condition for Q2 and Q3 are nearly unsatisfied, while the √7/√3 CDW still has lowest energy. Considering the broadened distribution of the imaginary frequency along the high symmetry path, we suggest that the structure is intrinsically fundamentally unstable and cannot be understood by CDW distortion. One may note that our Fermi surface model is afforded to make a prediction of the large funnel substance at the M point. however, the phonon line, which incorporates electron coupling and certainly has a large and broad peak at this endpoint, which suggests that the electron coupling is the driving force of the phonon instability at the endpoint. So for the future work, we should include the electrophonon coupling effect. Here I show, as shown in this formula, omega RPA is the normalized phonon frequency under the random phase approximation, and omega Q is the base phonon frequency, and D2 is the generalized specific electronic susceptibility, which combines the electron coupling matrix and the real part of the electron susceptibilities. With the decrease of the electron temperature, the phonon will suffer from their base values to 0 and even to the imaginary value when the temperature below the critical temperature. So the D2 can be regarded as a measurement of the phonon instabilities, which is obtained by integrating all the electron field. So how about we integrating all the phonon field? Can we obtain the indicator of the electronic instability, which may correspond to the CW gap? And this is just my assumption, and I don't know whether it's correct or not. So I was wondering if anyone of you is familiar with this related manifold theory and is interested in this work, so we can solve this problem together. That's all. Thank you.
Okay, thank you very much. Any questions from the audience? Yeah, Yang Tong, you can, I'm just going to read here by strain. Do you mean biaxial strain?
Yes.
Okay, so that's a quick answer. Okay.
So I had a quick question here. So this is the acoustic phonon mode, and you're saying the acoustic phonon mode exhibits a softening, a softening at this special wave factor. So actually your last slide, you look at the outlook, for example. So could you go to your outlook? Your last slide, you were there just now.
Last slide.
Yeah, so you're saying there was actually this softening going on here?
Yeah.
Yeah, so would you say that very last thing you said that you didn't really understand something? I missed it, sorry.
Yeah. So this T2 variable is obtained by integrating all the electron field in this actions. So I'm thinking about how about integrating all the phonon field. So can we obtain some indicator of the electronic instability?
Oh, I see. So you're calculating the phonon softening via a phonon self-energy that was coming from the electrons. And so you're wondering if there could be a similar thing happening for the electrons themselves. I see. Okay, thanks.
Okay, great. Do we have another quick question? Okay, if not, our next speaker is a faculty speaker from NUS, Professor Li Jinghua. I think he's here. Okay.
Hi, everyone.
Hey, hello.
So I'm going to share my screen right now.
Please.
Okay, let me start. Okay, first of all, I thank Professor Yang Guo and the rest of you for inviting me to this talk and to give a faculty presentation. So today I'm going to talk about my recent work, which I'm also doing with my group. So just for the outline, so my talk will be divided into two parts. So the first part will be about some non-Hermitian studies, which my group is doing. And the second part will be on some realizations of topological states, both Hermitian and non-Hermitian ones. And I will discuss both avenues that I've been trying on. One is on the electric circuits, which is the classical realization, and the other one will be the quantum circuits, which specifically we are not an experimental group, so we just sort of borrowed the IBM quantum computer on the cloud, of course. Okay, so first I'll talk about non-Hermitian phenomena. So when I talk about non-hermeticity, like one of the most common questions that I receive is that, is it even real? Like, does it even exist in real life? Yeah, I mean, of course, my answer would be yes. Yes, it exists. And it's not just sort of in the restricted sense as some people might think. So one sort of main way that people think of would be when you have a quantum system that is coupled to the external reservoir, where you have to use like Lindbladian formalism and other things. So that's one possibility. And of course, in the classical context, there's actually many more avenues that are possible. One is on just classical damping. So for example, if you have friction, your equation of motion will of course have to be non-Hermitian. And in photonics, there's actually even richer avenues which are also potentially or practically useful. For example, lasers. I mean, the very fact that they amplify means that they are non-Hermitian. And of course, in all the devices that we use now, including the hardware that Zoom is running on, would also contain transistors and like ablational amplifiers and all these active circuit elements, which are also non-Hermitian. So besides sort of this sort of a technological platforms, right? You can also use non-hermeticity to describe sort of a complex network phenomena. For example, like asymmetric random walks, or like say cellular automata for describing nonlinear kind of classical interactions. And of course, there are also radiation dam systems and so on. So yeah, my whole point here is just saying that there's a huge variety of systems that could be non-Hermitian. So let me now go on to some signatures of non-Hermitian physics. So the first, which is sort of probably the most commonly heard, would be exceptional points. So the idea is that when we have non-Hermitian systems, the energy spectrum can be complex. And as you know, when you represent something on a complex plane and you have complex functions, you can also have constructs like branch cards and branch points, right? So exceptional points are essentially the branch points in the complex energy spectrum. And when there's a branch point, we know that there are some multi-valueness with the energy spectrum. So that leads to some kind of if amplification effects, sensing effects, and other effects that there are many of those described in the literature. The second would be on the enlarged symmetry classes possible with non-Hermitian systems. This is also because non-Hermitian systems can have complex energy spectra. So instead of just a gap closing, say, on the real line, you have the complex plane. So for example, you can have line gaps where the energy gap sort of cuts between, let's say, two separate parts of the complex energy plane. Or you can have, say, something called a point gap, like what is shown here, where the spectrum kind of encircles some points. Of course, this is not possible in Hermitian systems because you don't have a complex energy plane. And another very interesting phenomena which has recently gained a huge following is a non-Hermitian skin effect. So essentially what happens is that there's an asymmetric gain and loss, which means basically it just means unbalanced or asymmetric couplings, and that pushes the states all onto one side. And this will be what I'll be elaborating on mostly for the first part of this talk. Okay, so what is the non-Hermitian skin effect exactly? So to understand it concretely, we can look at one of the simplest possible models. And by simple, I really mean like simpler than all your interaction like spin Hamiltonians in the previous talks. It's just like something with just nearest neighbor couplings, such that the couplings are actually asymmetric. So in this case, what I've drawn here would just be a case where the coupling from the right to the left would be 2, and the coupling from left to right would be half, so they're asymmetric. And in this case, it can be shown that, I mean, just plugging this into, say, Mathematica, you can show that the eigenstates all are like localized on one side. And not just that, we find that if you were to change the boundary conditions, the energy spectrum actually looks very, very different. So for example, when you have periodic boundary conditions, you find that the spectrum is a loop. I mean, it's an ellipse in the energy plane. You can see just by substituting e to the ik into this, and you see this should be an ellipse. But if you were to have periodic boundary, so open boundary conditions, you find that actually the spectrum becomes real, even though there's no sort of PT symmetry or any kind of symmetry, but the energy spectrum becomes real. It becomes a segment on the real line. So what is really going on here? Okay. So the hint is that when we have a periodic boundary conditions, you have translation symmetry, and you always have to sort of preserve the block form of the eigenstates. That means you can have like real, sort of non-real spectra, but the eigenstates, I mean, they still obey like a form like e to the ik, like before, and you get like just a usual complex spectra corresponding to the hoppings. But when you have open boundary conditions, what happens is that you can imagine that if you have a wave function, initial state, right, the state will be amplified more in one direction than in the other direction. So they will have to accumulate somewhere. They will get bigger. A state will just get bigger and bigger as it evolves until it reaches a boundary where it stops moving. I mean, because there's no more hoppings for it to continue being amplified. And when it stops, we know that the energy spectrum has to be real, because if it's not real, the complex part of the spectrum will just sort of indicate like a continual amplification. So the fact that the amplification actually sort of the directed amplification actually stops somewhere, so forces the energy spectrum to be real. So just now, the model that I showed was probably one of the most trivial examples that's easy to understand. Once you add a slightly more complicated hoppings, so for example, coefficient of 1 for the next nearest neighbor hoppings from the right to the left, and another different coefficient for left to the right for nearest neighbor instead of next nearest neighbors. So when you have sort of slightly more complicated unbalanced couplings that are between different distances, you can get much more interesting couplings. I mean, and much more interesting spectra. For example, like the Y-shaped OBC spectra on the right. And the PDC will be this loop here. So this is still the tip of the iceberg, because it can also be shown that when we would to sort of change the terms in the tight binding model hoppings to something more complicated, it is possible to get many other sort of very interesting kinds of spectral structures. Like you can have stars, and with some conformal mappings, you can get like groups of stars, or with some other kinds of hoppings that are currently being investigated, we can even get like different loops and so on. So this type of graphs or theoretic classification of structures, of spectral structures, is a new avenue of topology that I would say have not been really discussed in the literature. So this was first put up in my PRP paper last year, and right now, me and one of my students, Tommy, is investigating into even more intricate structures and an even more systematic way of actually classifying this type of graph-like structures in the energy spectrum. So as you can see, they are not restricted to just stars. They can take the form of, say, insects and so on. I mean, even many other like sort of pictures that you would think only appear in biological like journals, but no, they just come out from tight binding models. Okay. So some people might be asking, so what's the point of studying these intricate and funny looking energy spectra? So my answer to this is that when we have these branching singularities in the energy spectrum, we actually have a special type of phase transition. And these are actually gap phase transition. The reason is as follows. So usually, when we talk about a topological phase transition, because it's only when the gap closes where sort of the degrees of freedom in the different bands can meet each other and probably exchange discontinuously. But in this case, when there are sort of branching singularities, it's possible for the different branches to sort of just shrink and rearrange without actually having any gap being closed. And that is also how we can get, for instance, like discontinuous Berry curvature, as shown here for this particular model devised by us, which is called a non-Hermitian, like a asymmetric non-Hermitian Chern insulator model, where we have topological edge states that look kind of normal, but with the bulk bands that have some interesting structure in the complex energy plane. And this type of system actually gives us this continuous Berry curvature. And what are the implications? Well, that's something that we can actually measure if we have the experiment. So the measurement can be done through semi-classical transport of wave packets. I mean, we haven't done it, of course, because we are a theory group, but this is work in progress, and we are trying to work with collaborators on some semi-classical transport experiments where this continuous Berry curvature actually show up as kinks. They show up as kinks in the past because the anomalous velocity which come from the Berry curvature will suddenly sort of have a discontinuity whenever the wave packet passes by certain momentum points. So let me just highlight a few more interesting non-Hermitian examples before I move on to the next part. So one thing is that in the context of our nodal structures, we know that in a Hermitian nodal structure, we have surface states called drumhead states that fill up the interior of the surface of the nodal loop projection that's projected on the surface Brillouin zone. So in non-Hermitian systems, we can also do such surface projections, but because of the non-Hermitian skin effect, so the shape of the nodal structures will look totally different. And this is systematically studied in my paper here. So one comment is that if you were to study these models, you find that actually some of these tight binding models in the non-Hermitian case can be much simpler than in the Hermitian case. And the reason is because when you have non-hermiticity, you have more degrees of freedom in sort of defining your coefficients of the Pauli matrices in the two-band model. And therefore, it's possible to find much simpler coefficients that give rise to the same kind of nodal structure, the same kind of nodal knot or link. And let me give a more general, sort of a comment on non-Hermitian spectra. So previously, I've already talked about what happens when you have the concept of a gap in the Hermitian system. A gap is just what happens when you have two sort of bands that are disconnected in the real energy for Hermitian systems, and when the gap closes, they touch, right? And when you have a non-Hermitian system, the point is that they can touch in different ways to form different kinds of line gaps or even point gaps. And just now, as I mentioned, we also have the case C, where the gaps, so the bands don't really have to touch. I mean, the gap don't really have to close, but the bands can sort of internally reassemble among themselves in a discontinuous way to give you discontinuous Berry curvature and maybe discontinuous band metric and so on, band geometry. So I want to highlight another of interesting of our phenomena that we discovered in this Nature Communications paper, where there's something called a critical non-Hermitian skin effect, where what is sort of in between, so two sides of the phase transition, is something that is actually totally different from what is on the both sides. So in other words, it's something that is totally discontinuous, in the sense that in these other cases, the intermediate case is an interpolation of what is on both sides. but in this case, it does not actually have to be. And the most salient feature is that when we were to change the system size of the system, of the finite realization of such systems, we find that with different system sizes, we can get like very different phenomena. So for example, in this case, you have a huge point gap when you have a large 80-side system, and we have a 10-side system, you actually get a much smaller. Sorry, you get like almost a real energy spectra. And it can also be shown that you can get topological. In some other cases, you can get topological modes when you have certain system sizes and non-topological modes on other system sizes. So that means now we know that in non-hermiticity, there's a new concept of a size-dependent topological phase transition. And what about interactions and many-body effects? So it turns out that non-hermiticity also has a very pretty, I would say, non-trivial or even more non-trivial implications on such systems. So in this paper, we basically studied the Hartano-Nelson model, which is with asymmetric hoppings, just with fermions. And we realized that even at the level of free fermions, where they don't really interact except for the Pauli exclusion, they actually form a sort of new type of effective Fermi sea. The reason is because when you have fermions, right, they cannot all be sort of pumped to one side, even with the non-Hermitian skin effect, right? Because they can't all occupy the same boundary ring. So they will accumulate on one side. But when they accumulate on one side, right, it kind of looks like they obey a Fermi dilution, but that's in real. So it's from that this actually behaves like an actual Fermi surface in energy space if you were to define the effective temperature to be equal to the physical thermal temperature plus some nonlinear corrections between the temperature and the alpha, which is the hopping asymmetry. And now before I go on, I'll touch on the last idea, which is it actually applies to both Hermitian and non-Hermitian systems. And the idea is that when you have an interacting system with multiple particles, we can also consider what happens or how does this system look like in the configuration space where we have, say, one axis representing the position of one particle and a different axis, a different dimension representing another particle. So coordinates. So for instance, we can find that in multi-dimensional systems with, say, like many body interactions, we can understand it as a single particle system that is interacting, that's not interacting, but in higher dimensions. So in fact, this is also, one of the applications would be what my student Rachel has talked about previously, where we discovered new types of I'll say eigenstates that are not really skin modes, but they are just cases where the particles just are clustered with each other. I mean, they have clustered in each other with certain clustering properties because of this asymmetry, and that could be understood by mapping to a higher dimensional lattice. So now we are submitting this paper, with some other of my other students and we actually did a quantum computing implementation, which I will talk about soon. So now I will move on to talk about experimentally realizable platforms for topological systems. So many of these are realized with my collaborators, except for the quantum computing part, which we can do it through the cloud ourselves. So first we talk about the classical circuits, which are just, everyone knows what a classical circuit is. It's an electronic circuit. And one of the hallmarks is that it is a supremely versatile. Like, for example, you can make it into some kind of fractal shape, or you can make it into something that looks like a London subway map. And so we have a series of experiments on these kind of systems. Yeah. So just to give a flavor about why we expect circuits to be good probes of topological robustness is this. So everyone knows what the Kirchhoff's law is, right? So basically it's just a linear relationship between the current input that's input at any node and the voltages that are sort of at itself and other neighboring nodes. So we can easily put this into a matrix equation, right? I equal to JV, J is called admittance matrix. And if you were to invert this, we get G equal to inverse of J. So G is called a circuit Green's function. And the interesting thing is that if you were to calculate the impedance between 2 points, it can be shown that the impedance between 2 points A and B is given by this general formula where you sum over all the eigenmodes of G or J, and you divide it by the eigenvalues. So that with the numerator being the difference in the eigenmodes. Special about this formula, the reason is that yes, because we have a denominator in the spectrum, and the denominator basically means that if we have a reason like a physical mechanism where this Jn is sort of pinned to zero or pinned very close to zero for many different n's, right? We will get a large degeneracy. I mean, this large degeneracy will force the impedance to be very large. So indeed, one ideal candidate that we can think of straight away would be Fermi arcs, right? Because Fermi arcs, they are topologically protected and there are so many of them and they are localized in real space. So it means that if you were to have a circuit whose band structure has a Fermi arc, then immediately you are going to expect to have a very large impedance when you connect, say, 2 points. When you connect 2 points, and the 2 points is where the Fermi arcs actually do exist. So indeed, this is what we showed in the experiment in our paper. Yeah, so I have to mention that actually the non-Hermitian skin effect is also very amenable to electric circuit realizations, but there are also other platforms other than electric circuits. So one is on the photonic quantum walk by a group from China. And another one is using mechanical systems by a group from Europe. And for the circuits themselves, I had a few different experiments. I will talk about these too, and in the next few slides. So I know because time is a bit limited, so I'm going to go a little bit faster from now. So basically, the experiment in our Nature Physics paper is basically based on a non-reciprocal or non-Hermitian SSH chain circuit. So we have a non-Hermitian SSH chain where some of the hoppings are asymmetric, and we can sort of exactly reproduce it with the help of operational amplifiers. Yeah, so this unit cell corresponds to this unit cell and so on. And what's interesting is that when you do the impedance measurements and the band structure reconstruction from like sort of combining the data from many different impedance measurements, we actually managed to reproduce exactly the bulk boundary sort of correspondence breakdown. So for example, the PVC spectrum for some cases will be a loop. The OBC will be measured to be a line. And yeah, so there is, if we were to look at these cases, there's almost a perfect agreement between experiment and theory. And the reason is just because for circuits, it's kind of a mature technology where it is just not so non-trivial to achieve a high level of precision. And one of the sort of so-called potential applications would be on a non-local voltage. So it with some input current, and you measure the voltage, you'll find that the voltage is actually very large on another part of the circuit. Even I think this will hold even if the circuit is super large. I think, and that's because of the non-local nature of the amplification. So I also have to mention that this non-Hermitian skin effect is not just restricted to non-reciprocal sort of systems per se, in the sense that if you were to say combine two different systems and do two different non-reciprocal systems that are equal and opposite, and change the basis, it's possible to get something that's reciprocal but still having a bulk boundary correspondence breakdown. I mean, this is analogous to saying that even with time reversal invariant systems without breaking time reversal, you can get a quantum spin Hall effect by combining two like quantum anomalous Hall systems and doing a basis transform. Right? This is kind of analogous to that. So, and one application of this would be a pseudo spin filter, because in this case, certain kind of pseudo spins will experience the skin effect in one direction, and other pseudo spins will experience another kind of amplification in the other direction. Okay, so now I'm going to move on to another type of quantum simulation projects that we have been doing. So I hesitate to call it an experiment. I mean, compared to the previous works were all about experiments for the circuits, but in this case, well, it's kind of an experiment in the sense that we are simulating sort of quantum Hamiltonians in the actual physical sense. Like, yeah, it's not just on a classical computer, simulating on a quantum computer, but I'm sure many people would attack me if I say it's an actual experiment. So anyway, for those of you who are not familiar with quantum computation, I have to say that, okay, so recently, actually in the last few years, there have been a few different publicly accessible quantum computing platforms. So we chose the IBM platform because it's the most accessible to us. In fact, it's accessible to everyone, actually, to the public, through this website. And it's also very user-friendly because it even has a GUI interface for beginners where you can just drag and drop different gates which represent different Pauli matrices, and you can just create like a quantum circuit just like that. So the quantum circuit is basically a sequence of quantum gates, like sequence of Pauli matrices. So but of course, if you want to do something that's more non-trivial, you will have to write a code to kind of generate a quantum circuit and do different operations like measurements and the collapse of the wave function. And you can use a Qiskit platform where you only need to use, basically you only need to know how to use Python for programming. So one caveat is that the machines that have higher fidelity and with more qubits are only accessible by institutional subscription. Although, I mean, those of you, who are from NUS, I guess, will surely have this subscription. And of course, whoever collaborates with institute with subscription will probably have. My feeling is that actually everyone here probably has access already. Okay, so actually, I have to say that the IBM Q quantum computer is not really just used for topological simulations, of course. And in fact, if you search an archive, there has been hundreds of papers that already talk about IBM Q applications, but they are usually talk about, say, like error correcting codes or different computer science applications or like optimization and sort of maybe hybrid machine learning algorithms. So I would say that logical phenomena, the IBM quantum computing platform is still at its infancy stage. And the reason is because at this point of time, or at least until the very recent past, there isn't really that much that can be done yet. So the reason is because of the very limited number of usable qubits, and also the significant gate errors, which I will elaborate more on later. So basically, the idea is that if you only have a bunch of qubits, that's not too many, and you have significant gate errors, which are limitations to the computational complexity. There are really not many sort of good models that we can realize from most of history. So one thing is, if you would look at the recent papers, or rather the few existing papers before our paper on the topological phenomena on quantum computers, these are the few papers. People like to use a cluster Ising model because it is a very simple interacting model with interacting three interacting spins. And the point is that on the quantum circuit, right, an interaction is in principle not really more complicated than a single particle hopping. I mean, in the sense that if you were to do exact diagonalization on a classical computer, you need to implement something much more complicated. You need the ED whenever you have interactions. But for a quantum circuit, you actually don't. I mean, the complexity is about the same. And also for quantum computers, right, the implementation of sort of time-dependent Fouquet driving is actually almost, I would say, of equal level of complexity as a static Hamiltonian simulation. Because when you simulate a static Hamiltonian, you do a successive gate operations for the different sort of unitary steps. But when you do a simulation of a time-dependent Fouquet driving, you do exactly the same thing, just that every step is different. So unlike in other systems like, say, co-atoms and all this, where there are technical limitations to Fouquet driving, in this case, not so much. And I think for these reasons, this is why such papers were already published in PRL for such states. So in our recent work, actually we realized a far more complicated system. So it's called the extended Kitaev chain. Yeah, and we could achieve this because of our access to larger and more accurate quantum computers. So for example, the IBM Q Paris, which although it is probably not accessible to anymore right now. So what we did was that we implemented this type of systems using some tricks in circuit recompilation. So I have to mention that usually when people think about getting a spin chain, which is what the hardware of a quantum computer is based on, from an interacting fermion chain, right? We use a Jordan-Wigner transform first. And then we also use a technique called the cauterization approximation to split the many bodies of interacting Hamiltonian into chunks of sort of unitary operators, which are like just where you just have up to, let's say, two spin gates. But the problem is that that usually gives us a very deep circuit. In this case, for Hamiltonian of this complexity, we'll need at least thousands of gates. But if you look again, right, so you see that for every gate, we actually have an error of the order of probably about 0.1 to 1%. And it just means that if you have more than a couple hundreds of gates, basically all you get will just be nonsense, right? So what we did was the more sophisticated technique of circuit recompilation, where we have ansatz for the quantum circuit, which can be optimized to fit this Hamiltonian very, very well. Yeah. So with the simulation of such Hamiltonians, we could for the first time realize not just the SSH topological realization, but also on actually other types of systems like other types of topological modes, like say the D-class topological modes, and with next nearest neighbor hoppings and so on. So I would say that this is the first time where sort of topological modes, they are protected by sort of lattice, sort of single particle lattices, lattice is realized in topological systems. More details, you can read this paper. Yeah, by me and my group. And before I end the talk, I just want to highlight one last example. So this is a work in progress. And basically what we did was that we realized the chiral topological transport of a Chern lattice on the IBM Q quantum computer. So a moment of thought will give you a kind of a confusion, which is that we know that for a Chern lattice, right, usually to see anything more meaningful, we'll probably need, let's say, an L times L system where L will probably be like maybe 8 or more, right? And it just means that the number of sites that we need would be probably of the order of 10 to the 2, like, or maybe 50 to 100 sites at least. So there aren't, right now at this point of time, there's actually no quantum computer that has this number of reliable qubits. So how did we do the formalism was for Hermitian systems? And what we did was that we actually mapped the 2D system, which is non-interacting, into a 1D system that is interacting. So which means that we actually map an 8x8 lattice system into a one-dimensional system with 2 16 qubit systems. And I think soon this will, I mean, depending on our journal submission, so this paper will be out soon. Or if you're interested, you can always get it from me. So to sum up, I would say that non-Hermitian systems are all around us, and the non-Hermitian skin effect leads to a lot of different interesting phenomena like discontinuous Berry curvature, non-local signal response, and it also leads to new types of nodal structures and hybrid modes. And in fact, if you were to look at the literature, you can see that we also create new paradigms for the negative entanglement entropy and with IRC and op-amp circuits. And more recently, for the Hermitian part, at least on the quantum computers. So thank you. That's the end of my talk.
Okay, thank you very much for the very interesting talk. Yeah, we have time for questions, of course. Any questions?
Connection, the couplings between them are actually created not equally. So which means that by default, we actually already have a disordered system. And in fact, if you run the same code on different days when you initialize the qubits differently, you also get a different result, slightly different result. So I'm saying that quantum computers are actually intrinsically disordered already. And it's more about mitigating the effects of disorder that is more of a problem than actually having disorder.
So are you saying this is a very natural system to study disordered systems, but you just don't have the control of tuning the disorder?
Yeah. So I mean, if you would ask me to study a disorder effects, then of course we will still want to include our own disorder in a way that is more tunable. Or of course, we can also study do very careful study of the calibration of this IBM Q.
Do we have any knowledge of the disorder in the quantum computers? If we know some of the properties of these disorders, and that's pretty much all we need, right? Say the standard deviation, is it white noise, or do we have any knowledge of that?
I would say that we can always measure this. I don't think they gave, as in, are you saying that do they release the results to us, or?
No, normally when we do simulations on classical computer, we also have a random number generator to generate the disorder, right? So the way we tune the disorder is by tune for example, the distribution range, the amplitude, and all those parameters characterizing a set of random numbers. That's all we need to simulate a disordered system. Can we do this with the quantum computer as well? If we know some knowledge of the intrinsic disorder in a system, then that's pretty much all we need, because we need a random number generator anyway. for the classical computer, right?
Well, in this case, if you're talking about the intrinsic disorder, I would say that is more like just the noise in the hardware, which is not easy to control. But if you really want to sort of simulate, but there's a separate question, which is that if you really want to generate random numbers from the quantum computer, of course we can do it. I mean, like Google did it and say that there's a quantum supremacy. That means that could be a separate task that the quantum computer is very good at doing.
I'm just saying, is it possible not to do that task because it's already intrinsic disorder? Can you actually design a very simple system and run it on a quantum computer? Then by running it, you can study the property of the disorder in the system.
Sure. I mean, that's of course possible because we can just say, take the system, maybe we choose those qubits that are already not so good. And yeah, of course, it's possible to do some kind of calibration and run it we can run it many times over different days and measure all the, maybe even the correlation functions pertaining to this. Yeah.
Okay, good. Any other questions?
Hi, I have a question regarding the discontinuous Berry curvature. So can these Berry curvature be discontinuous in both point gap and line gap systems?
So your question is that whether the discontinuity depends on whether there's a point gap or not, is it?
Yes.
Okay, so if we look at I go back to the slide, right? So in this case, this system is actually so usually when we define the Berry curvature, we usually sort of use a gap system, right? Because so the bands don't touch and it's well defined. So in this case, it is already a gap system. But if you were to have a point gap, I would say that it's still possible to define the Berry curvature because we can still sort of like define we can still cut the system into two if we want to. But then now the signature of the discontinuity will not be so clear. The origin will not be so clear because it could be due to the way that we join the two bands, or it could be due to the fact that it could be due to the rearrangement here, right? So
I see. Okay, thank you.
Yeah.
So a related question, for this non-Hermitian Chern model, you have these edge states. Are these edge states also robust against small perturbation?
In this case, yes. In this case, in fact, we designed the system so that the edge, that means the OBC, like topological states, they are all like real. So which means that if you were to, so you can imagine that if you do an experiment, maybe with a circuit, it can already be done. You'll find that these chiral modes actually behave in a way that is quite similar to the usual chiral modes. Just that if you were to kind of probe the, if we were to probe their sort of the wave packet transport, you will be able to find some kinks at some point, but otherwise they behave quite similarly to actual